Welcome to Physics with Mr. Brazil. Today we're going to study centripetal acceleration in the horizontal direction, and this is part one. This is a three-part series, so link below will be the other three videos, so if you want to see those also. Now, to start, centripetal acceleration has to do with an object moving in a curve, and anytime an object is moving a curve, the velocity is tangent to that curve. And therefore, the velocity vector is changing. Anytime you have velocity vector changing, you have an acceleration. And in this case, the acceleration is towards the center, a sub c. So centripetal acceleration is equal to velocity squared over r, or 4 pi squared times r over t squared, where t is equal to time. So the time that the object is going around that curve. And if you might be wondering, well, what is the force? Well, the force is straightforward. Centripetal force is just mass times AC. And just like in your other force calculations, it'll be just mass times velocity squared over r, or mass 4 pi squared r over t squared. Super straightforward. Actually, so straightforward. Let's look at the question below. A 2.5 kilogram tethered ball is whirled in a horizontal circle at 5.5 meters per second with a radius of 4.00 meters. So what's the tension? Always start with a free body diagram. So here's our ball. Here's our cord, and there's a tension. And also there is another vector, the weight. The weight is straight downward. But this is a horizontal circle, so let's just sketch that so you get an idea. It's just a horizontal swirling around. Well, there is no other forces in the x direction other than centripetal acceleration and the tension. So the net force in the x direction for horizontal is T equals mass times centripetal acceleration. All we have to do is just write our variables first, as always. So centripetal acceleration, velocity squared over r. And since this is 5, wait, I went too fast. So let's get that fixed. We got the mass, so 2.50 kilograms. Always slow down and make sure that you square the velocity. A lot of students, when they first start doing this, they forget to square it for some reason. So our answer for this particular problem will be 18.9 newtons. So pretty straightforward calculation. Now let's consider a car going around a turn. That's our second problem. And here we have friction. Things are a little bit different and things we need to talk about. First of all, this particular car is going to go around a radius that's 50 meters, and it has a coefficient of friction of 0.351. Let's start with a free body diagram so we can get an idea of what we're doing. Well, we have our normal force upward, and let's make this our front view before I get too far ahead of myself. So let's call that a front view. So this is the car coming at us. Then we have the car's weight downward. And since it's making a turn, I'm going to say it's making a turn towards the right. Its centripetal acceleration is towards the center. Notice also, though, the friction is going to be also towards the center. So the force of friction is towards the center. It's important that as a beginner, you understand there are no forces where I'm writing the X. There are no outer forces, even for the tethered ball. So look up top here, no forces. Even for the first example, no forces. So where there's the red X, there are no external forces in that direction. So in other words, no centrifugal forces. They do not exist. So let's take a top view of this car going around a turn. Okay, so we got our turn. Here's the car, and that means the centripetal acceleration is towards the center, and so is the friction. Friction is pushing, see, as the velocity vector changes, the friction helps helps push the car into the turn. If there was friction where I'm going to put the red X, then you have exceeded the friction, the coefficient of friction, and the car is now moving out of the straight and crashing into something else. So friction is always towards the center. There are no centrifugal forces. That's important. It's kind of a tough thing for folks to understand. So let's look at our net forces here in the X direction again. Well, we have the friction force going towards the center, but we also have centripetal force at the center. Therefore, if we just write our equations, so mu equals Fn, that's for frictional force, so you should have gotten that. And then we have mass times centripetal acceleration. Write this out a little further. So since Fn is equal to the weight, so I'm going to write mg, that's for Fg. And then mass times velocity over r. Well, the mass drops. And to solve for velocity is just a little bit of algebra. You're going to end up with, I'm going to put it up here, v equals mu gr, and we square root the whole thing. So we want velocity all by itself. Well, let's put in some numbers and see what happens. We have 0.351 times 9.80 meters per second squared. And the radius is 50. So 50 meters. And we'll square root that. And punch that in the calculator, and we're going to get 13.1 meters per second. So if you go any faster than this, you're going to see the coefficient of friction, and the car is going to slide right out. Okay, so check out the other two videos. Those will be discussing vertical spinning objects, and then the third video will be regarding angles within that vertical object. Okay, keep studying physics and don't give up on this stuff. It's awesome.